Welcome to EDU World Space.
Here note that the given coordinate system can be rotated about its axis until the line of acting of the wrench lie on one of the axes. Let's choose z-axis over here. This can be done because the wrench or a vector and some point are independent of the coordinate system. They exist with or without the coordinate system. We only define the coordinate system to help us deal with the vector operations. Changing the coordinate system only changes the component of the vector and the coordinates of the point. Also, it's important to mention that the real space Cartesian coordinate system represents real space is isotropic, meaning invariant to the rotation of the axis. Also note that now we can choose how we position our force that acts on the point A, and we can choose where we can hit our second point and the orientation of the force that acts on the second point. Since we need to prove that it can be done, we only need to find one case and not a general solution. We can look at the task for help. We see that if we position the second point on the y-axis and if we make our two forces perpendicular to the y-axis, we can definitely solve that problem. But we need the additional condition that those two forces must be perpendicular. Let's mark the point B somewhere on the y-axis and solve the system for the equation. We assumed that both forces A and B have only x and z components. So we can write Fa is equal to ax0 az and Fb is equal to bx0 bz. Since those two forces are equivalent to the original situation, we know that they must add up to the original force. So Ax plus Bx is equal to 0. So Ax is equal to minus Bx and Az plus Bz is equal to R. We also know that they must produce the same couple. So Ra cross Fa plus Rb cross Fb is equal to M. Solution of this cross product gives us AAZI minus AXK plus BBZI minus BBX is equal to MK. Compiling both the sides, we get AAZ plus BBZ is equal to 0 and minus AAX minus BX is equal to M. Let's solve the second equation first by substituting AX. So we will get Bx is equal to M upon A minus B, and from this we can write Ax is equal to minus m upon a minus b. Next, let's find az from the first equation and then put it into the equation that we got in the first segment of the solution. So from that we can get az is equal to minus b by a bz and bz is equal to ar upon a minus b. Returning this into the expression for the az, we get az is equal to minus br upon a minus b. Finally, let's put everything together. So, force Fa is equal to minus m upon a minus bi minus br upon a minus bk, and force Fb is equal to m upon a minus bi plus ar upon a minus bk. Next, we have to make them perpendicular by choosing the right distance b, since it is the only parameter that we can change. So, to do so, we can write Fa dot Fa is equal to 0. So from this we can get B is equal to minus m square upon ar square. Note that B has to be negative for our forces to be perpendicular. If we return this into the force equation, we get Fa is equal to minus m upon a plus m square upon ar square I minus m square upon ar square r upon a plus m square upon ar square k, and Fb is equal to m upon a plus m square upon ar square I plus ar upon a plus m square upon ar square k. Or when we simplify, we get it in the another form.